Hello, I'm Paul Beckwith, and this is part 3 of my mishmash on significant climate change happenings, occurrences that have been in the media that I've tweeted out in the last few months. And this is kind of an overall summary of some of the key things that are the most important in my opinion. So I'll just get right back into it. Please watch parts 1 and 2 if you haven't. Okay, so this is just showing this is the air temperature in the Arctic by rank in the satellite era from 79 to present day, updated through April 2019. And the number in the boxes is the rank. So 1 is the warmest. Okay, so 1 here. So this would be the warmest January over the whole record. You know, the second warmest, the third warmest, and so on. So that's done for each month, and you can see this is a strong El Nino year, and you know, we're getting more and more reds as abrupt climate change with rapid temperature warming proceeds. Now, climate models are very important, but there's a huge over-reliance on climate models in climate change reports, especially the Intergovernmental Panel on Climate Change. So, you know, we are getting better with models, but looking out the window and seeing what is actually happening in reality is crucial. I mean, the models only take you so far. And, you know, if they don't predict accurately what's happened in the past or predict what's going on in present, then we don't have much confidence that they'll do a good job. Basically, they're underplaying things. So, you know, what's happening, I mean, everything's happening faster than expected. So the models are struggling to keep up. But this article from Yale is about using artificial intelligence. Can it be used to build better, smarter climate models? Right? I mean, this machine learning code is starting to go into climate models so they can capture details hundreds of times more efficiently than traditional programming. And this should lower the uncertainties of how climate will respond to rising carbon dioxide, and hopefully it will capture, you know, regional feedback effects, such as, you know, most importantly, the Arctic, huge Arctic warming in a better way to have better overall prediction. Now, methane is a huge issue, obviously. Methane's a potent greenhouse gas. This is the latest observations. This is a trend over since early 80s. So there was a very rapid rise here, 11.5 parts per billion per year. Then that tapered off to 2.8 on average, slowed down to almost 0 here. And then since about 2007, it's been rising fairly rapidly at 7.05 parts per billion per year. Methane is not accurately, it's not considered enough in the climate model. So in order to have any chance of, you know, being anywhere close to 1.5 degrees or 2 degrees, methane has to be dealt with. I mean, there's lots of, methane's basically natural gas, and fracking is actually bringing natural gas out of the ground to be used to, you know, which is basically bringing methane out of the ground. I mean, there's some methane dissolved in oil, so, you know, as the oil is brought to the surface, then the pressure, of course, is greatly reduced, and the methane can bubble out of the solution, and it's just flared off at a lot of locations, or it's just released, you know, directly to the atmosphere. But, you know, we're getting, the world is becoming, we're getting these torrential downpours, and we're getting wetlands, and we're getting rainfall in the high Arctic, and that's, you know, of course, all of these things are feedbacks which greatly increase the amount of methane that is released, that can be released to the atmosphere. This is interesting, an interesting map showing if all of the Earth's groundwater was pooled above ground, how deep would it be? So less than a meter is the light blue areas, but there are areas, you know, from 1 to 50 meters, and greater than 50 meters of groundwater is some of the darker areas. So this is very important to This study was the first to map all of the Earth's hidden groundwater, because it's often, overexploited. When there's drought in regions, for example, it allowed a lot of wheat and stuff to be grown in the Middle East for a while, and then the groundwater levels all dropped, and that all had to stop, right? So lots of irrigation for crops relies on groundwater when the precipitation on the in that region is insufficient for the crops. This was tweeted out about 8 months ago. I did a video on jet stream center of rotation to shift 17 degrees south. Okay, so this is a key. I'm always trying to figure out what will happen when there's a blue ocean event. How will that affect different regions? How will that affect crops? So basically, the idea is that the center of cold is, right now it's near the North Pole, but offset a bit towards Greenland because of the massive Greenland, how far in latitude southward it extends. But with no Arctic sea ice, of course, the only cold mass in the Arctic will be Greenland, and the centroid of Greenland is 73 degrees north, which is a shift of 17 degrees southwards of the North Pole. So if that center of cold is really the center of rotation of the jet streams, and the jet streams will completely shift, and that could lead to very common large troughs over North America, right, as it gets offset. And we're seeing right now large troughs over North America. It gave us a very cold winter, and it's giving us a very cold spring. So this could be these patterns could become more and more common in a world with no sea ice or very little sea ice, and the rotation, the center rotation of the jet stream actually shifting, and that will disrupt, everything on the planet, basically, directly the northern hemisphere. Okay, this is an interesting image. Speaking of the jet stream trough being stuck over North America, going deep into the U.S., this is National Weather Service warnings for floods and flash floods since 2008. Okay, the lighter the color, the lighter the blue, the more flood and flash flood warnings since 2008. So we've got the Mississippi River coming down here. There's this area here is very, very, huge numbers of warnings here. It's called Flash Flood Alley, if you like. And clearly, it's no surprise that a lot of the flooding is from the Mississippi and the tributaries and so on, that are feeding into the Mississippi. This is showing, and this is an interesting map showing tornadoes and hurricanes in the U.S. Since we're getting lots of tornadoes at the moment, and we're concerned about the hurricanes. Also hurricane season starts June 1st, runs through November 30th, and the U.S. Hurricane Center just came out. They said it would be sort of an average year, 2 to 4 major hurricanes. That's Category 3 and above. 5 to 9 hurricanes, and something like what was it? 15 to 19, something like that, storms, if I recall right. Anyway, the Canadian Hurricane Center did the same thing. It's supposed to be going to be an average year. All that can just mean that they really don't know what's going to happen, so they just say it's an average year. So this is the tornadoes since 2004, wind speeds as you go to greener and greener. So you can see the track. Some of these are very long track tornadoes. Most of them are shorter length, but you can see kind of the distribution. And down here, lots of activity in Tornado Alley. And these are the hurricanes and how far inland that they're affecting things. So we've got Sandy here, we've got Irene and Florence and Irma, which came up in Florida. Luckily, it missed the, Miami. If Irma was tracking right up here along for the east coast of Florida, if it maintained that path, it could have been $1 trillion in damages. Instead of that, in 12 hours before it hit, it veered to the left and came over into the Everglades. And Michael and what's that? Ivan, Katrina, of course, is here. And then we can talk about Rita and Ike in this region and Harvey in this region. And remember that these storms are starting to behave much more differently when they come ashore. So Harvey, with the jet stream slower and weaker and not carrying storms as fast, some of these hurricanes are coming ashore and they're meandering around. They're staying sort of half over the ocean, half on the land, like Harvey. And it took 4 or 5 days of that before Harvey moved off and dissipated. Hurricanes, they need the 26.5 degrees Celsius water temperature or more to gain energy as they go across the ocean. When they come ashore, they generally dissipate quickly. But if the ground is saturated, and of course it's very warm, so the water sitting on the ground will be very warm, it can act almost like a brown ocean, it's called, to the hurricane. So the hurricane, when it goes ashore, there's so much water on the ground that can evaporate and feed the storm. The storm doesn't dissipate as quickly as it used to. So parts of this region from Harvey, Texas, they got something like over 5 feet of rain in some places during that 4 or 5 days of the storm. Like just phenomenal. Of course, Sandy was a freak combination of a tropical storm, a hurricane, combining with a nor'easter, and it couldn't, as it was moving off the coast here, it couldn't turn right like every other hurricane does. Some have turned right 270 degrees and come ashore, but Sandy couldn't go north, couldn't go east, so it turned sharply almost 90-degree west, and of course, overtopped the flood protection in New York City. So, it drowned all of these residential areas. So new bylaws came in. Those houses had to be all raised 9 feet. So if the owners didn't do it when the house was sold, in order for people to get a mortgage, they'd have to have insurance, and in order to get insurance, the house would have to be raised about 9 feet high. We've had significant flooding, in large parts of Canada, including Ontario and Ottawa, where I am. And those people, that's the second time, and didn't happen last year, the flooding. It happened 2 years ago. So lots of people flooded again, and they have to do something. Take all the insurance money, jack up the houses. I did a separate video on that. Now, this paper was very significant, about the extinction. About 1 million species are expected to go extinct out of the 8 million that we know about. This is extinction since 1500. Look at the spikes up for amphibians, mammals, birds, reptiles, and fishes. This is the decline of species since 1980. Look at corals plummeting, mammals, birds, amphibians, cycads. All across the biodiversity, the scales of biolife. Many species just vanishing. This is certain different species groups. The percentage threatened is the blue line, and these are critically endangered, different scales of risk to the species, and you can see, the cycads. We're just losing species like crazy, and this is all related to climate change, but there's also a lot of other pressures like habitat destruction and plastics in the environment and chemicals and not enough habitat, you name it, it's bad. Now this is a very interesting, this is how global warming is changing temperatures on the Earth. So this is a year. This is the percentage of the Earth's surface exposed to a global temperature anomaly. So this is what you can see is as the years advance, we're getting more and more warming, and this is the distribution of the warming. So not everywhere will warm equally, but the mean is increasing, right? There's always going to be a distribution about that mean, and that tells you a bit about the statistics of the variation of temperature. So what you can see is the warming going on, and I'll continue this in my next video. Thanks.